Welcome everyone to lecture 3 of the GR course. Today's topic is geodesics, and this will build on what we learned about tensors and covariant derivatives in the last couple of lectures. And in fact, today we are going to quickly recap some of the things that we learned about covariant derivatives and then build upon that to discuss about the covariant derivatives. So let us start with a quick recap. And I will keep my eyes on the chat, but I will not be able to answer every question immediately, but I will try to answer every 15 or 20 minutes. So there's one question, maybe I can start with that. So you made a statement about how two kinds of derivatives are related by a tensor. Can you state it again? And yeah, I'm going to quickly recap what I said about covariant derivatives. All right. Recap of all right. So what did we learn? So first of all, we kind of convinced ourselves that GR should describe the time evolution of space. Um, and in the story, the dynamics of this evolution corresponds to studying the space-time of geometry, the geometry of space-time. So basically what's going on is that so you have space, it evolves with respect to time, and putting all of this together, you find a 3 plus 1 dimensional object, right? Which is the space-time, this red thing. Right. So now we are motivated to study geometry. And then a natural question is how to describe geometry. I mean, we all have some intuitive notions of what various low-dimensional geometric objects look like. For example, we know what a two-sphere looks like. We know what a two-dimensional plane looks like. But first of all, in GR, we have to talk about four-dimensional spaces, and we have to talk about pseudo-Riemannian spaces. So they have one direction where distance is negative, and also the spaces that we're going to study may not be as nice or simple as a sphere or flat spaces, right? So we need a more robust way of talking about geometry. And so the hint that we got is that we can learn a lot about the geometry of a space by looking at what happens when we move vectors around, or more generally tensors around. So for example, if we were on a sphere, then we could draw these lines, which are kind of straight lines on a sphere. And by moving vectors kind of in a parallel way, we see that we do not end up at the same. So here, this is facing this way, this is facing this way. So we can kind of parallel transport in two different directions. And we see that we don't end up with the same vector. Whereas if we were on a flat space, then we would end up, if we draw straight lines or any lines, and you parallel transport vectors, Anyway, the idea is that you can kind of gauge what's happening locally in the geometry by transporting vectors in various directions. So what I'm saying right now involves words like parallel transport, which we are going to define more rigorously in a moment. Uh, okay. Um, and so this then leads us to studying covariant derivatives. There's a question, so can you always slice spacetime as the way you showed at the very beginning? I don't think so. At least not in a way that keeps your space particularly nice. But I am simplifying things. Okay, so now we're motivated to study covariant derivative. So we already have a derivative, which is the partial derivative. This is going to be the shorthand notation for partial derivative with respect to one of your coordinates. But so what we observed is that this is a good derivative. But not a covariant map. So it does not map tensors to tensors. Okay, so that's a problem. So we try to fix this problem by postulating some properties that we want our covariant derivatives to have. So what are the properties? So the first property is that, so we want covariance, meaning that, so this symbol, which we are calling just del, this should map PQ tensors to P P+1 tensors. And then in order for this operator to be a legitimate derivative, it has to satisfy certain properties. So for example, linearity, which simply means that if you have sum of tensors, you can distribute. And if you have some constant numbers multiplying these things, they just come out of the derivatives. We have the Leibniz rule, which shows you that how to distribute derivative over products of tensors. So if you have something like U, and of course, this generalizes. If you have more indices, you just put them wherever they were. Okay. All right. Yeah. So then we made the comment that these conditions do not uniquely identify derivatives. It is possible that there are more than one derivatives. And then we made the claim that if there are more than two derivatives, if there are more than one derivatives, then let's take two of them. So let's say delta mu is one of them, and delta mu tilde is another one. then their difference when acting on any vector, or more generally a tensor, but I'm going to write down formulas for vectors for the sake of simplicity. This is always going to look like the following. Okay. Where they are completely independent of t. And the point here is that here you do not have any derivatives of t of any order. Okay. So it's just t and something that's independent of t. All right. And if both of these derivatives are covariant, then this is going to be a tensor. If one of them is not covariant, then you still have this formula, but it will not be a tensor. Okay. So we did not prove this formula. We cited some reference. So actually, I'm mostly following Sean Carroll's general introduction to GR book, but this proof is actually not in that book. Maybe I can mention some of the sections of the books that I am mostly following. Yeah, so let me mention it now. Yeah, this will be recorded, so it's fine. So what are the references? So for example, Carroll section 2.1 for the equivalence principles. And then from section 3.1 to 3.4 for the derivatives and geodesics. And for this particular statement, you can see the book. It's just called General Relativity by Wald, and you can look at section 3.1. So Wald is a bit formal, so he writes down all the properties of the covariant derivatives, and he tries to prove some of them, which is enough for this course. Okay. So a very nice consequence of this property is that we can always take as a reference derivative operator, our partial derivative operator, right? Because this is true for any derivatives. They do not have to be covariant. So this allows us to compare the covariant derivative of a tensor with the partial derivative of the tensor. And then we know that there will be something like this, and then the tensor itself. And when our reference is this partial derivative, this is written with the symbol gamma. And it's called the Christoffel symbol, right? So this is Christoffel symbol. Okay. And again, since this is not covariant, this is not a tensor, that's fine. So the point here is that associated with any covariant derivative, there is a Christoffel symbol which measures how much this derivative differs from just the ordinary partial derivative. And then by imposing the constraint that this has to transform as a vector under a coordinate transformation, we were also able to figure out the coordinate transformation rules for these Christoffel symbols, which I don't know if I need to write it down again, but maybe I can just mention something. So let's say that we are changing coordinates from x mu to x mu prime. So in new coordinate systems, you have these Christoffel symbols. So mu prime, lambda prime, and they are related to the old coordinate systems by something that is completely tensorial. I hope that by now you are all familiar with the tensorial transformation rules. And then there's an additional term. Okay. So this part involves the original Christoffel symbol in this coordinate system, and then this term which is independent, but this is what makes it not a tensor. So there's a question. So since it is not a tensor, C nu mu rho is not written in tensorial form since the contraction doesn't occur. Could you refer to the contraction for C or gamma here? By contraction, are you referring to this contraction? If yes, then I am still assuming that repeated indices are contracted. That is, I'm always assuming that repeated indices are contracted, whether these indices belong to tensors or not. Meaning that there is an implicit sum here that rho 1 goes from 1 to d. Okay. All right. Yeah, and again, just as a reminder, I am writing down formulas for operators acting on simple vectors, but you can derive these formulas more generally. So for example, on an arbitrary, so I'm not going to write down how the covariant derivative acts on a completely arbitrary tensor, but let me write down how it acts on a 1, 1 tensor, which will be enough for you to figure out the general case. So let's say, so what happens if you have two indices, one contravariant and one covariant? So you always start with the partial derivative. Then you add a term for the upper index. And you add a term for the lower index. Okay. Now, notice that some of you may have seen this kind of formulas before, and often you will see that people write down basically the same symbol twice, but perhaps with a minus sign. But I want to point out that that does not necessarily follow from the properties of the derivatives that we have defined so far. All you can say is that there's one symbol for the upper indices and one symbol for the lower indices. And these two can be completely independent of each other, but they just have to transform with the same transformation law, okay? So this gamma tilde will transform exactly like this, where you have gamma tilde here, and there's a gamma here, which will have a tilde, okay? As long as that is satisfied, this is a perfectly valid equation. Okay. Now, we still have not proved that, in fact, there are any covariant derivatives. Although it's by now, it should be kind of obvious in the following sense. So a manifold is composed of coordinate charts, right? So you have some coordinate chart here and some other coordinate chart and some other coordinate chart. Okay, you have to have enough so that it covers the whole manifold. Now, so what this tells you is that you can take a coordinate chart and write down any quantity basically that has three indices, okay? Completely arbitrary. And then, so once you have defined a gamma here, you can define a, let me give names to these coordinate charts. Let me call them U, V, and W. Now, once you have completely arbitrarily chosen a gamma here, you can define a gamma here by doing a coordinate transformation from U to W, right? So, so this is gamma U. I don't know what is a good notation, maybe gamma U. And then you have gamma V. And in the intersection of these two coordinate charts, you have some transformation. And you define this gamma V by imposing that it satisfies this coordinate transformation when you go from here to here. All right. And similarly, you can go from here to here and define gamma W. So all we have to make sure is that once you go from here to here, and then you go from here to here, it's the same as going from here to here, right? So starting from gamma u, you do some coordinate summation, you go to gamma v, and then you go to gamma w by doing another coordinate summation. Let's say here you had x mu, here you had x mu prime, and here you had x mu double prime. But it could go directly from here to here, right? Yeah, because there's also an intersection. And you just have to make sure that these two are the same, which you can check explicitly, that coordinate transformations commute. It doesn't matter which way you do these transformations. Okay. So now that we can kind of see that there are infinitely many connections. Okay. So another comment about notation. So these symbols will also be referred to as a connection from time to time. But something to keep in mind is that connection also refers to the full derivative itself. This is a slight abuse of notation. People use the word connection to refer to both the Christoffel symbol and to the full covariant derivative. Okay, hopefully it will be clear from the context which one is being used. Okay, and they're basically equivalent, right? Because if you know this, you know this, and if you know this, then you know this, because this is always fixed to be the partial derivative. There was a question, the expression doesn't have an extra gamma. I think I missed when this question arrived. So could you remind me which expression you are referring to? Covariant derivative of t. So something like this. So you're asking why is there gamma tilde? The expression doesn't have an extra gamma. Well, so this expression does have an extra gamma, which is this one. And the reason that there is a tilde there is because I'm saying that these gamma and this gamma, they do not have to be the same. They can be completely different. As long as they both transform by this law, it's fine to write down this formula, and this will be a covariant derivative. Okay. So a priori, these gamma and gamma tilde are different Christoffel symbols. I think Carroll does both, and at some point he proves that if we impose certain constraints, they become the same. So let me now mention what those constraints are. So as I was saying, that there are infinitely many connections. So we have the freedom to choose certain connections that are particularly nice. So the point is that we can impose even more constraints than the ones we have already imposed. So for the sake of keeping track of the conditions, let me number some of these conditions. So what did I say so far? Actually, because the linearity and Leibniz are fine. I can refer to them as linearity and Leibniz. So those will be 1 and 2. So let us put more constraints on our connections. And here it is important to emphasize that we can put these constraints. It does not mean that we have to, but it is simply the fact that by imposing these constraints, we will get some particularly nice covariant derivatives that will be easier to deal with computationally. So what are the constraints that we are going to put? So number 3, after linearity and Leibniz, we're going to assume that covariant derivative commutes with contraction. What do I mean? Suppose you have a tensor with contracted indices. Okay. You can have more indices, but you have at least 2 that are contracted. So this would be the same as first taking the derivative, and then contracting the indices. Okay, this seems like a reasonable thing to impose on our connection. And also, we are going to impose that covariant derivatives act as partial derivatives on scalars. Okay, so for example, del mu phi, where phi doesn't have any tensorial index, so it's just a scalar. This should be the same as just a partial derivative. All right. Okay. They both look reasonable, but again, there is no a priori reason why you have to impose them. In fact, you don't have to impose them, but if you do, the Christoffel symbol will have some nice properties. In particular, we can show that if we impose these two constraints on top of linearity and Leibniz, then these two things that we wrote down, gamma and gamma tilde, they have to be related. Okay. So this is a consequence. We'll write it down. As a consequence of Leibniz plus 3 plus 4, these 3 and 4, we get okay. All right. So this is a consequence of these two additional constraints. So now if you look back at this equation, so you can now replace this gamma tilde with negative of gamma. And then this starts to look more familiar with the formulas that you perhaps see in textbooks. Right? Okay. And so Schonfeld actually proves this, so I'm not going to repeat the same proof, but you can look at, say, parallel equations 3.12 to 3.15. So he very carefully demonstrates that once you have these additional constraints, these two Christoffel symbols have to coincide. Okay. So there's a question. So applying the covariant derivative over mu to a tensor with n upper and m lower indices, there will be n plus n plus 1 terms in the derivative. Yes, that is correct. All right. Now, we still have not mentioned something that's very important and very prominent in any study of general relativity, which is the metric, right? Because usually whenever we want to talk about a manifold, maybe you guys have seen more formal definitions of a manifold in your tutorials. So recall that a manifold is not necessarily defined with a metric. You just need some kind of differentiable structures, right? But still, a metric is kind of very intrinsically connected to the study of GR in particular, because a metric gives you a notion of distance on your spacetime, yeah, which is, of course, extremely important. So we will always be working with a metric. So when we have a metric, we want our connections to play nicely with the metric itself. So what do we mean by that? What we mean is that we are going to impose even more constraints. But before we talk about the metric, let me mention another important quantity that we can talk about before talking about the metric, which is called torsion. I will be brief because we're not going to actually use this thing. So the first observation is this. Suppose gamma mu nu rho is a Christoffel symbol, so it defines the covariant derivative for it. Then, uh, Also notice that so far we have not said anything about the symmetry property of these indices, right? They do not necessarily have any symmetry property. But the observation is this: if this is a Christoffel symbol, then so is this with the indices reversed. And so why I say that? I say that because the Christoffel symbol is defined by basically its coordinate transformation. Um, Maybe I do need to write down what this part is. So now let's look at the index structure. So these two indices, mu and lambda, so they are contracted with mu and lambda. And then here you have mu prime, lambda prime, which appear here, right? And these two things, they obviously commute. You can change their position. It doesn't change anything. So if you swap the positions of these two indices, you can swap the positions of these two without introducing any sign or anything. And also here, so these mu and lambda, so they appear in these two partial derivatives. And again, partial derivatives commute. So there are no problems with commuting the order of mu and lambda. So the point is, if this tensor satisfies this transformation rule, then the tensor that you get by swapping the indices, it will also satisfy the correct transformation rule with the tensorial part, and this part remains exactly the same. Okay. And since this transformation rule is all that defines the Christoffel symbol, if this is the valid Christoffel symbol, then so is this. Okay. And now again, recall this property that the difference between any two derivatives is this kind of linear map. And if both of them are covariant, then this is a tensor. Now, the Christoffel symbols define covariant derivatives, right? So take one Christoffel symbol where we have mu nu and another Christoffel symbol where we have nu mu. And then take the difference. And then what you'll find here is going to be a tensor. So the point is, so let's say this Christoffel symbol defines a covariant derivative delta, and this defines a covariant derivative. I don't know how I should write it. Let me call it just delta bar. So what I mean here, this a Christoffel symbol implies this also a Christoffel symbol. Okay. Now the difference between these two objects is going to define a tensor. This is unfortunate notation. Let me use U because I'm going to use T for this particular tensor. And this is called a torsion tensor. I mean, the name of this tensor is torsion. Okay. And as you can see, associated with any covariant derivative, there is going to be a particular torsion tensor, right? Because any covariant derivative comes equipped with a Christoffel symbol. From any Christoffel symbol, you can define another Christoffel symbol simply by changing the two indices, by swapping the positions of the two indices. And then by taking the difference, you can get this tensor. Now, for this course, what we're going to say is that we are only interested in connections such that, so this is going to be our number 5 constraint, which is the torsion is 0. So we only work with Christoffel symbols that are symmetric in these two lower indices, because then if you solve their position, you get the same thing, and so these two are the same, and then the difference is 0. All right. And again, there is no obvious reason why you have to consider this simplification. It's just that it is a great simplification. You can do GR with non-zero torsion tensor. Then it's just that the formulas will be more complicated. And for the basic understanding of GR, it suffices to consider torsion-free connections, which is what we're going to do in this course. But just keep in mind that these are not the only connections. There are connections with torsions, and they are important for GR. All right. Now let us introduce the metric. Okay. Now we introduce the metric G mu nu. And once we have the metric G mu nu, we are going to impose yet another constraint on our Christoffel symbol, 6, which is that we want the metric to be covariantly constant. So why do we want this? So we are actually going to see one application of this momentarily. But so roughly speaking, so at the moment we can say that if we have this, what will happen is that the inner product between two vectors, two vectors, strictly speaking, two vector fields, so inner product at different points, it will only depend on those two vectors basically, and not on the metric itself. So meaning that if you have two vectors whose norms are constants, then their inner product is also going to be a constant, which kind of intuitively makes sense. But so we have introduced a lot of constants on our Christoffel symbol, right? So we started with basically two, the linearity and Leibniz, these two, which were our number 1 and number 2, which were very reasonable. And from there, we saw that there were many Christoffel symbols. So we felt optimistic, and we imposed a bunch of other constraints to be particular. So then the question remains, I mean, we have to ask ourselves again, are there still one or many or zero connections left that satisfy all of these constraints? Okay. Now the answer is much more interesting. And the answer basically is that, so as a consequence of all these 6 constraints, there is a unique connection satisfying 1 through 6. Okay. This is very nice. Now we have no more degrees of freedom. There is one canonical connection that we can use. So how do we know that there's a unique connection? Well, the easiest way to show this is to actually derive the connection. Right? So we can actually take all of these constraints, all of these things, and we can basically compute what that connection is. So let me sketch how this is done. And for the detail, again, you can look at Sean Carroll, who does this carefully. So basically what happens is that, and it's actually a very easy computation. So this is going to be our starting point. So let's start from here. So the covariant derivative of the metric vanishes, right? So we have this equals to 0. Now, well, these indices are arbitrary. So we can take, say, cyclic permutations of these things. This is also 0. And so is this. Right? I mean, they're basically the same equation, right? But um, well, we have a formula for how covariant derivative acts on tensors. So, for example, in this case, you're going to have something like this. Okay. And similarly, you can write down formulas for this one and this one, something and something. And if you now take this and subtract these two from this expression, and basically you are taking the sum of these two and subtracting that from here, well, you are still just subtracting sum of two zeros from a single zero. So what you're left with is still zero. But what you find is that in order to get this expression, you have to use the fact that because of this torsionless condition, your Christoffel symbol is symmetric in the lower two indices. So here you have some gamma, here you have some gamma, and you have to swap the positions of some of the indices in order to get to this expression, because that will allow you to cancel some of the expressions, right? So here we are using the torsion-free connection. And we already started with this covariantly constant metric condition. This you can easily solve, right? Because you can multiply with G inverse. So this is just a G without any derivatives. So if you multiply by G inverse, so what I mean is that take G rho, so multiply this with G rho sigma. So from G lambda rho, G rho sigma, you will find the Kronecker delta. Lambda sigma. So then, okay, then you sum over lambda using this Kronecker delta, which replaces this lambda with sigma, right? So if you do this, you do the similar things for the other terms. You mean you just multiply but now you cannot contract because here the partial derivatives are acting on the metric. So what you find at the end is that gamma nu. Okay. So this is an important equation. And so what we have basically done is that we have shown if we impose all these six constraints, then gamma can be written uniquely in terms of the metric. Okay. And there is only one solution to these equations. So there is only one gamma that satisfies all these conditions. So this is a constructive proof that there is a unique Christoffel symbol that's metric compatible and torsion free. All right, so this is a good place to take a pause, I think. And let's see if there are some questions. So what does the torsion-free nature implicate about the space-time manifold? Does it affect the physical laws in any way? Okay, so, this question about torsion. So what does torsion physically mean? It's a torsion means that the basis vectors of any coordinate form closed structure. If a coordinate has torsion, the grid into it doesn't form, there will be gap between tips of the basis vector. Yes, that's correct. So giving torsion a physical meaning is a bit complicated. Maybe there are, but I'm not that familiar with it. But to me, torsion is a bit hard to visualize because it's not something that we see in our physical experience. Uh, Similar to how in quantum mechanics is difficult to visualize, right? Because it's not part of our experience. We can do mathematics, it's fine. So for example, you can write down formulas for curvatures, you can write down geodesic equations, etc., everything. And And it's just that all of those formulas will have these corrections by torsion. But physically, is there something nice to be said about it? I have to look it up. I will see if I can find some nice physical meaning of torsion, and if I do, I will mention it in the next lecture. Do we always have to stick to this connection, or we can have different connections based on different scenarios? We do not always have to stick to this connection, but so notice that, okay, so suppose you have a connection that doesn't satisfy all of these properties. So, well, maybe this is the last condition that we impose, right? So suppose you have a connection that doesn't satisfy this. Then it gets a bit complicated in the sense that how you measure distance on a manifold does not play nicely with how you transport quantities from one point over space-time to another point over space-time, right? So then there are basically two different stories, one based on your connection and then one based on your metric. Mathematically, there's no problem with it, but well, physically, we are interested in the story with the metric because in all physical scenarios, we want to measure distances. So then basically what the story with the metric is the same as the story of the Kirchhoff connection that's metric compatible. Can you show a geometric analog for QED covariant derivative? We usually think of this as more of a mathematical result from interaction Lagrangian instead of a geometric point of view. Can you show the analogy? Aren't you going to talk about parallel transport? Yes, I'm going to talk about parallel transport. So the question about QED, can you show a geometric analog for QED? I'm not sure I'm following the question. So what do you mean? We usually think of this as more of a result from interaction Lagrangian. I mean, are you asking what is the relation between the covariant derivative that you see in QED and the covariant derivative that you see in GR? If that is a question, then they are basically the same thing for different contexts. So the covariant derivative that you see in GR is what allows you to parallel transport tensors from one point of your spacetime to another point of your spacetime. And we're going to talk more about parallel transport in a moment. Now, the tensors are not the only kind of things that you can define on your spacetime. You can also define something called spinors, which are again some kind of functions on your spacetime with components, but these are not the same components as a tensor. And you can also talk about parallel transporting spinors from one point of your spacetime to another point of your spacetime. And in order to do that, you need another connection, which is the connection that you see in QED. But all of these connections have some compatibility conditions, and yeah, they're all instruments for doing parallel transport of things. Okay, so I think this is a good time to go to parallel transport, which is the main reason why we were interested in this covariant derivatives anyway. Okay, so what is parallel transport? So roughly the intuition is that so suppose you have some spacetime. So this is your spacetime. You have some quantity at a point x over spacetime, or x mu if you have more than so you have some coordinates. And then so here you have some quantity, right? So let's say you have some phi of x. And this phi can have one index, one or more indices. Okay. And if this is a field defined on your spacetime, then this will have some value at each point, right? So let's say that you have another point. And then, so let me use slightly abstract notations. Let me call this point just P and this one just Q. So this is P. So here you have Q with indices. Okay, so perhaps we want to compare these values, okay? And this may seem like an obvious thing that, okay, you just compare whatever the values of these tensors are at that point. But if you think a bit more carefully, it becomes less obvious. To see why that is the case, let us first consider the case that actually is obvious, which is the case of a scalar function. So this is your spacetime again, and this is a point P, this is a point Q. If you actually have a scalar function, phi of P, phi of Q, and let me also consider real first. It doesn't make any difference. It can be complex, but let's say real, real scalar. Then this is simply a real number, right? And this is another real number. And we can always unambiguously compare two real numbers. One is going to be larger than the other, or they can be equal, or whatever. There's no ambiguity regarding which one is larger, which one is smaller, what the difference is, right? It's obvious. So let's be a bit more quantitative. So suppose we have this function at P. So I may use two kinds of notation for a point. So P may refer to a point in an abstract sense, and then X mu may refer to the coordinates of that point. And strictly speaking, I should write X mu of P to refer to the fact that these are coordinates of this point, but the notation may get too heavy if I keep doing that. So let me write Fx, okay, for now, let me write Fxp. Plus, let's say that point Q is rather close to P. And we can kind of say that this is P plus delta X, where delta X is a very small distance from P to Q. So then this is something like this. And we can use Taylor's formula. So this becomes f of x, or just the value of your scalar field at point P, then delta x mu, delta x mu, and then phi, right? Derivatives evaluated at P. So derivative evaluated at P, x mu P. So there was still a question about covariant derivative. So the covariant derivative we deal with in QFT arises when we demand the Lagrangian to be invariant under some transformations, but not geometrically as we deal in GR here. I think the previous question was, can we think of them also geometrically? So the answer is yes. So basically all covariant derivatives are defined geometrically as a way to parallel transport things. It's just that if you want to define the covariant derivative that's responsible for parallel transporting spinors, then you have to go into some differential geometry, which may not be required background in undergrad. So may not be introduced in QED, but that is the origin of all covariant derivatives. So maybe there is some connection between gauge redundancy and geometry of manifolds. Absolutely. There is indeed a connection between having the Christoffel symbol as a connection and gauge redundancy. So the gauge transformations here are going to be diffeomorphism. So these coordinate transformations. What did you mean by connections? I didn't quite catch that part. So by connection, I'm referring to both the Christoffel symbol and the covariant derivative. These terms are all interchangeable. So the covariant derivative equivalent to a connection, equivalent to a Christoffel symbol. Okay, yeah, they're the same. Okay, so this is just the Taylor series plus other terms. But we are assuming these to be small, so we can kind of ignore the higher order terms. Okay, so what is going on here? So you have the value of phi at P, and then you have the value of phi at a nearby point, which is just a delta x distance away from P. And these two values differ by a term that looks like this, right? So basically, you can kind of see that this partial derivative is what is responsible for transforming the value of your field phi at P to the value of phi at another point Q, right? So roughly speaking, so this operation, this partial derivative contracted with the small vector del x mu, this transports the scalar field phi from P to P plus del x. Okay. Now, obviously, if there are higher order terms that you cannot ignore, the meaning when delta x is not infinitesimally small, then you cannot really say that, because then it's not just this thing that transports, but you also have to worry about all the other higher derivative terms. But when delta x is small, this first order differential operator is what takes you from one point to another point, right? Okay, that's fine. But what about vector fields or more general tensor fields? How do we compare values of those fields, or how do you parallelly transport them? Well, so here we have to kind of postulate some things. So what is the generalization of this kind of expression that we can write down for tensors? The most obvious generalization is, in fact, so we should replace this with something that's covariant. Now, why is that? What was wrong with the partial derivative? Well, the problem is, if this is not a scalar, then this is not a vector or a tensor, right? And then this contraction, this does not transform nicely under coordinate transformation, which would be a problem, right? Because on a manifold, there is no unit coordinate. You can describe the same positions from the perspective of different coordinate charts. So let's look at the picture of our manifold. So suppose you are transporting something from here to something here, right? Now this you can describe using the coordinate of this chart or coordinate of this chart or coordinate of this chart. And the statements that we make about parallelly transporting things, we want them to be the same basically in all coordinate charts. In particular, actually, okay, so we have been using the term parallelly transporting things. So what is being parallelly transported? What does parallel mean? So this in general is not, I mean, this vector field phi is not parallel unless this is 0. So parallel basically means that two things are the same. So if phi takes the same value at both P and Q, then we will say that, okay, then now phi is being parallelly transported from P to Q. And when does it happen? So if this is the same as this, that means that this is 0, right? So for a scalar field, for a scalar phi, parallel means that its partial derivatives vanish. Okay. And so now you can see why it is important to generalize this to the covariant derivative. Because we want to say that for a vector V, parallel should mean the covariant derivative of the vector is 0. Okay. Now, what would go wrong if we use partial derivatives here? What goes wrong is that suppose you have the partial derivative of a vector equals to 0 in one coordinate chart, right? So in U. So again, so recall that we have these three coordinate charts, U, V, and W. And suppose this equation is true in this chart. If you go to this chart, would the analog of this equation still be true? The answer is no, this will not be true. So you will, if you do a coordinate transformation of this quantity, you will have two terms, right? So one is the tensorial term where you multiply this by a bunch of things. All of this vanishes because this vanishes. But then you have some terms that involve, well, basically the terms that are not covariant, right? And those do not necessarily vanish. So you will end up with the situation that in one coordinate chart, you have something that you would call parallel, but then in another coordinate chart, it's not parallel. But okay, the choice of coordinate chart is completely arbitrary. So is it parallel or is it not? It becomes ambiguous, right? That's why any statement that we want to make, that we want to hold in all coordinate charts, those statements must be made with the covariant derivatives. So this is the most natural generalization of this parallelity condition. So we must say, so this does not work, and we must stick with this condition. So, okay. Again, so just as a reminder, so far we have been talking about transporting things infinitesimally, right? So from P to just P plus del X, so that in a Taylor expansion, we do not worry about higher order terms. So basically, if you have a vector field or any tensor field or whose first order derivative vanishes, then that thing is being parallelly transported at small distances. So suppose from X, if you have some direction u mu, which defines a small distance x plus u, then if you have this condition that u mu delta mu v nu equals to 0, that means this vector v of x is being parallelly transported to vx plus u. Maybe I can draw a picture. So suppose here you have this vector v at x, and here you have this vector v at x plus u. And then we can say that, okay, so this is parallel to this. All right. So this basically means that this derivative vanishes. All right. Let's see. So if you have any question about this, so this is an important concept, right? So let's see if it's clear. What did you? So I don't see any new questions. Okay. All right. So let's move on with the covariant derivative. So let's check something. Suppose we have two vector fields, u and v, both covariantly constant. Okay, so what does it mean? So it means that at a point, regardless of which direction I'm moving, these vectors are being transported parallelly everywhere. So maybe this is u. And this is v. All right. So intuitively, we would like to say that the inner product between these two vectors, so from our intuition about Euclidean geometries, the inner product should only depend on the norm of these vectors and kind of the angle between these things. And if they are being parallelly transported everywhere, then the inner product should not change. So is that true in GR? So let's take the covariant derivative of the contraction between two vectors, u nu, v nu, which are constants, covariantly constants. So what is this? This is g nu rho, u nu v rho. So notice that, so we have to distribute this covariant derivative over tensors, right? So del mu g u rho. Okay, so we use Leibniz rule. And we also distributed covariant derivatives over a tensor that had contractions. We also use the commutation with contraction. And we have defined this U and B to be covariantly constants. So this term vanishes, this term vanishes, because this is 0 and this is 0. And this term only vanishes if we have this condition that the covariant derivative of the metric is 0. So this vanishes by our last condition, by 6. So overall, when all of these conditions are imposed on the connection, this vanishes. So now our intuition holds that if two vector fields are parallel, then the inner product is covariantly constant. Okay, so this is why this condition 6, that the covariant derivative of the metric vanishes, is important. Okay, so far we have talked about parallelly transporting things at a small distance, but what about at a finite distance? So now we are really moving things far apart. We start from some point, and then we follow some curve very far away, maybe, and then we reach another point. And suppose you have some vector fields lying around, or really any tensorial field. Okay? So suppose there is some kind of field, so meaning that locally, so suppose you have some vector here, you have some vector here, you have some vector everywhere. And you can ask the question, is this vector here parallel to this vector here, right? That was our original question. And this is a rather subtle question, because how do you compare two vectors? If you're in Cartesian coordinates, so let's say this is our Cartesian coordinate. So if you have two vectors, something like this and something like this, so what you really compare is the projection of these vectors along these axes, right? And you see whether, and you just basically compare these real numbers that you get by projecting these vectors onto these axes. In other words, you write your vectors in components. So U1, U2, UD, these will be some components of a vector. And then you have V1, V2, VD. This will be another vector. So this is a vector, this is a vector. And you basically compare the values of these components. Well, okay, so that's fine. But what you have to worry about now is that this vector is here and this vector is here. And there is no obvious basis for these axes, right? So it's not like there's some God-given axis here and God-given axis here and similarly here and here. And then you project this onto these two axes and you project this onto these axes and you compare their values. Because these choice of axes are really the choices of coordinates, right? Because this was X and this was Y. And here you may have a completely different coordinate system. So whenever you have these potential for changing your coordinate systems from one place of your spacetime to another place of your spacetime, there is no obvious way of comparing two vectors. And that's why we have to build all this machinery to define what parallel transport even means. So what we have said so far, that we said that a vector is being parallelly transported if its covariant derivative in a particular direction vanishes. So this applies only when these 2 points are infinitesimally close. I mean, so close that you can roughly say that, okay, you can basically use the same coordinate system. So the same axis that you had here, you also have here. That is definitely no longer true if these 2 points are really far apart. Okay, but the nice thing about transporting these things is that a line, regardless of how long it is, uh, you can always break it down into small pieces. And if you break it down into sufficiently small pieces, then each of those pieces will be infinitesimally small and basically a vector, straight line. And then you can say that a vector is being parallelly transported along the line if its covariant derivative remains 0 everywhere on this line. Okay. So let me draw a zoomed in picture. So suppose this curve is some maybe zoomed in version of this. So if you zoom in here, maybe you see something like this. Right? And then what you do is that you break this into small pieces. And when I say small, I really mean infinitesimal. Okay, you do this everywhere so that you can basically say that this distance is just a tangent vector from this point to this point. And this distance is just another tangent vector. This is just another tangent vector. So this is kind of like a triangulation of a curve by small straight segments. Okay. And then suppose I have a vector here, which is u. As long as the covariant derivative of this u along each of these direction at each of these points remains 0, I can say that this vector is being parallelly transported along this whole line. Okay. To break down what I'm saying even more, so let's say this is P1, this point is P2, this is P3, P4, and so on. And these tangent vectors, so let's say this is V1, this is V2, V3, V4. So these subscripts, they are not vector indices. I'm just saying that it's just part of the name of this vector. So these vectors called V1, this vector is called V2, and so on. Now, I will say that U is being parallelly transported along the curve if the covariant derivative vanishes everywhere, right? So V1 mu covariant derivative mu u. So this is being evaluated at P1 if this is 0. And if, say, V2 mu evaluated at P2 if this is 0, and so on and so forth. Okay. So basically what is happening is that you have to say that U is being parallelly transported along the curve if, so in other words, so for any tangent vector, how should I write tangent vectors? V is fine. V mu delta mu U equals to 0 everywhere on the curve, where you have to identify V with the tangent vector, tangent to the curve. Okay. Now, I have to introduce a notation for a curve in order to do some computations. So what is it? Okay. But before I do that, let me see if there are some questions. These are some technical stuff, so maybe some things may be a bit confusing. Okay, so if U a directional vector with respect to is V a directional vector with respect to proper time? If the answer is yes, then what does considering another parameter lambda do? So the answer is actually no. U does not have to be a vector with respect to the proper time. It can be the vector with respect to any parameter of the curve, right? Okay. And yeah, so I'm going to define the curve with a parameter, so maybe it will be clear then. In other words, is parallel transport invariant transformation of the tangent vector parameter? Yes, it is invariant. It does not rely on your choice of parameter. Between 2 points, will there be a unique curve for performing the parallel transport? The answer is no. If you choose 2 points, then in between them, there will be many paths, right? So for example, I drew this black line, but it could have many other paths. And there is no guarantee that parallelly transporting a vector along different paths will give you the same result. In fact, in general, they will not. You will end up with different vectors. However, if 2 points are extremely close, infinitesimally close, in fact, then there is a unique path connecting the two, which has to be this tangent to, basically the straight line connecting the two. But this is a very rough statement because you have to really define what you mean by infinitesimal before you can say that there's a unique vector or a tangent vector connecting the two. Otherwise, it doesn't make any sense. But I am relying on intuition at the moment. Is there any specific condition where covariant derivative doesn't vanish while transporting and parallel transport no longer becomes applicable? Well, in general, if I give you a vector field, so suppose I just give you some function u, some vector field that depends on your spacetime, right? Its covariant derivative is not going to vanish anywhere with respect to any other vector, right? Then if you take some other vector and you compute this covariant derivative, it's not going to be 0. So a generic vector field is not parallelly transported from point to point. And simply pointing out when we can say that a vector is being parallelly transported. So a vector that is being parallelly transported is basically equivalent to a vector that's constant along the line, right? So unless you have a constant vector field, it's not being parallelly transported. The choice of curves matter. Yes, absolutely. The choice of curves will. So on flat space, the choice of curve will not matter because on a flat space, regardless of which curve you choose to parallel transport your vector from one point to another, you will end up with the same final vector. But the hallmark of a curved manifold is the fact that the choice of curve that you choose to parallel transport your vector from one point to another point dictates what the final vector will be. So depending on whether it came from here, maybe it will look like this. But if you come from this path, it will look like this. So covariant derivatives use Kirchhoff symbol to solve the problem of parallel transport in partial derivatives. Yes, exactly. So now let us be slightly more precise about what we mean by a curve. But let's see. I still have to. Yeah, I think it's fine. Okay. So what is a curve? We are using this word a lot. So suppose this is your manifold, right? And so intuitively we know that what a curve is. So a curve is just some lines in your manifold that goes from some point to some other point. So some initial point Pi to some final point Pf. But mathematically, so what is so we can say it like this. Each point in your spacetime has some coordinates, right? So this point has some values of x mu. So maybe x1, so here maybe x1 equals to 1.2, x2 equals to negative 4.5 or something, so on and so forth. So the basic idea is that at every point, the coordinates x1, x2, or x mu will have some value. And these values will change as you move along this path, right? So basically, a path can be defined by these values of your coordinates, basically, as you move along the path. Okay, so you can say it as follows: that a path is in M is a collection of functions x mu, function of a single parameter lambda. Okay. So by collection of functions, I mean that you have each component of this coordinate is a function, right? So you have x1 lambda, you have x2 lambda, and in higher dimensional manifolds, you have more. And so lambda here at the initial point may be 0, and lambda at the final point may be 1, but these values are arbitrary, so they can be anything. And as you move along this path, so lambda monotonically increases from 0 to 1, and the values of these coordinates also changes, which is what I was saying earlier, that maybe here we have some values, here we have some other values of the coordinates. So that's it. So these functions define a path from one point of your spacetime to another point. Okay. So if this is how we are defining paths, so then how do you write tangent vectors? So suppose at this point, okay, so a tangent vector is something like this. And we can kind of, if we zoom in on the tangent vector, so then this tangent vector is, roughly speaking, the difference between this point and this point, right? So what does it mean? So it means that, let me give some names to these points. So let's say this is Q and this is Q prime. But again, we have to remember that Q and Q prime are very close. So what's happening then? So you have x mu Q minus x mu Q prime. This is very roughly speaking, the component of this vector, right? And then you should divide this by the distance again. So again, this should be in quotation mark because anyway. Because we really only care about this difference when this distance is very small. And as this distance becomes small, this also becomes very small. So if you don't scale, then this will just vanish. But after you scale and then you take the limit, that this distance goes to 0. So then you can kind of say then, okay, so whatever this quantity is, this defines this vector. But of course, this is nothing but the total derivative of del x mu, dx mu, d lambda evaluated at the value of lambda. What should I say? So let's say lambda 0. So this is the value of lambda at Q. So I mean, kind of you have to use your intuition here. You can see rigorous definitions in textbooks, but what I am trying to kind of motivate is that we can identify the tangent vector at any point with the derivative of your coordinates with respect to the parameter of the line evaluated at the value of the parameter that corresponds to that particular point. Okay. So if we do that, then the condition of parallel transfer, so this thing, so which we were saying that here you have to identify this V as the tangent to the curve, right? Because these are all these vectors, the tangents. So now you can write that as dx mu, d lambda, the mu, what was the vector? V. No, U. Okay. So this defines a parallel vector along the line or on the curve x mu lambda. The curve defined by this set of functions of one parameter, right? Recall that we were defining a path in your space defined by a set of functions of one parameter. Okay. All right. So now we can define two very natural and important notions. So one is the notion of a straight line. And the other is the notion of the shortest line between 2 points. So we have basically all the tools needed to define these two concepts, and these are, well, obviously very natural concepts to understand in any geometric setting. But before I do that, so are there any questions? So we need a curve so that they stay parallel. So I think this was a response to the fact that I said that if you parallelly transport, actually, I'm not quite sure what the question means. I mean, so you may not be able to find any path along which a given vector field is parallel. All right, so let us now define these two concepts. All right, so let's start with the straight line, okay? So how should we define a straight line? In case of flat geometry, we have an intuitive idea of what a straight line is, right? So suppose this is flat. So a straight line is really just a straight line. I'm not going to define what it is because, again, I'm going to rely on intuition. But observe that this has the property that at any point, so let me draw the tangent vector, okay? Now, you can kind of convince yourself that this tangent vector itself is being parallelly transported, right? Because if I transport this from here to here, it becomes this vector. If I transport this one step ahead, it becomes this vector, right? So this is going to be our defining feature of a straight line. That a straight line is such that the tangent vectors themselves are being parallelly transported. And notice that this is not always true. By always, I mean this is not true for any arbitrary curve. So in flat space, let's take a curved line. So intuitively, we can already see that this is not straight. But so what about this criteria that we set up? So a tangent here is this, right? And if we parallelly transport this tangent to this point, it will be this. But is this the tangent to this line at this point? No. The tangent to this line at this point is this vector. Okay. So what's happening here is that this vector, which was tangent here, if I parallelly transport this along this line and it comes here, it is no longer tangent to this line. But here, if I parallelly transport this tangent vector anywhere, it will again be a tangent to this line. Okay. So this is how we want to define straight line. So as our definition of a straight line is, so a straight line means that the tangent vector tangent to the line is parallelly transported along the line. Okay. And this is based on what we observe in flat space, that the tangent to the straight line, if I parallelly transport it along the straight line, it remains tangent to the straight line. Whereas the tangent to a curved line, if I parallelly transport it, it no longer remains tangent to the curved line. All right. Okay. So this is our criteria. And how do we express it in using symbols? So recall our definition of a parallel transport. So here we were saying that a vector u is being parallelly transported along a line defined by this x mu as a function of lambda if it satisfies this condition. And this is the tangent vector, right? So if we can find a curve defined by a set of functions x mu of lambda such that the tangent vector, again, recall that this is the tangent vector, itself is parallelly transported. So I can put the tangent vector here again. And if this remains 0, okay, then this implies that this is straight. All right. Okay. So this is going to be our definition. And so notice something. So we are not deriving this relation, right? We are kind of defining what it means to be parallel. And then we are simply expressing that in terms of symbols. Now, our definition is not a completely random definition. It is based on physical intuition, but it is a definition nonetheless. It's not something that we have derived. It's something that we have defined. And this is us expressing our definition in terms of symbols. So a curve defined by a set of functions of one parameter lambda is called straight if those functions satisfy this differential equation. All right. Okay. So this again is an important equation, and so we can actually break it down. So for example, by breakdown, I mean that we can write it in terms of the partial derivative and the Christoffel symbol. So if we do that, so what we find is okay. So this, of course, is an important equation. I should remember to use colors. So this is our straight line equation. Right. So the first thing that we can observe that this is indeed consistent with what we see in flat space. So in flat space, your Christoffel symbols will vanish in Cartesian coordinates. So you will not have this term. So your straight line equation simply becomes that the second derivative of these functions vanishes. So meaning that these functions are linear. And so if you plot a linear function, you will find a straight line in flat space. But in curved space, it will look more complicated. All right. So we have our straight lines, but what about the shortest path? And this will be the last topic we discuss today. So let's see if we can finish it. The shortest line, when we say shortest line, we have to specify the initial and final point. Right? So the shortest line between 2 points. Now on flat space, we don't have to separately consider this, right? Because the shortest line between any 2 points, so let's say this point and this point, is the same as the straight line between these 2 points. But is that true in curved space? Well, it seems like there's something that should be true, right? It has kind of an intuitive aura of being right. But obviously in curved space, things are not obvious. So we should check whether it is true or not. Okay, so there's a question. So do you mean a geodesic by straight line? No. So by geodesic, I mean a short line. So this is going to be the geodesic. Thank you for the question. I forgot to mention what I mean by geodesic. So this is geodesic. So a geodesic is the shortest path between 2 points. Now the question is, so what is the main difference between autoparallels and geodesics? I think in GR they correspond to the same thing, but beyond GR, like torsionful and non-metric compatible theories of gravity, they do not coincide, aren't they? That is correct. So the autoparallel, so yeah. If we have torsion, these two notions will actually not be the same. Yeah. Actually, I'm giving away the answer in this case. So okay, so basically the answer is that if you don't have torsion, then the notion of straight line will coincide with the geodesic or the shortest path. But if you have torsion, they can fail. But we still have to check, right? It's not obvious that these two are the same. So how do we check that? Or okay, so when we talked about straight line, we had to define what we mean by straight line in curved space, right? Because it wasn't obvious. Similarly, we have to define what we mean by the shortest path between 2 points in curved space as well. This actually is a bit more intuitive than the definition of a straight line. So suppose we have a curve connecting 2 points. If I ask you what is the distance between these 2 points along this curve, well, you should be able to divide up this curve into smaller pieces. Then you compute the distance from here to here, you compute the distance from here to here, here to here, and sum all these distances up, right? So intuitively, the idea is that the length of a curve can be measured by measuring the infinitesimal distances and adding them up, okay? So what is the distance from here to here, assuming that these two things are infinitesimally close? So if they are infinitesimally close, we were saying that there should be a tangent vector at this point that points to this other point, right? So let's say that this tangent vector is u. And you also have the metric here. You have the metric g mu nu. So you can measure this distance by measuring the norm of this vector. So what you're measuring is that you compute this g mu nu, u mu u nu, at this point. So let me also say that this point maybe is called P, then you are measuring this at P, all right? So this quantity tells you the length square of this, okay? So you take the square root. So now this is the length of this vector. So similarly, you compute the length of the vector here, you compute the length of the vector here, and then you add up all these lengths. Now, so remember your calculus class, this will simply become an integration, right? So what is going to happen is that, and we already established that the expression for the tangent vector is something like this derivative. So when we say this u, what we really mean is that dx mu d lambda evaluated at some point lambda naught, that corresponds to this p, right? The value of lambda at point p is this lambda naught. So overall, so the length of a curve, we can write this as an integration. And so you have to go from, say, lambda 0 to, let me use lambda I and lambda f for initial and final. So lambda I to lambda f. Okay. I mean, this has an intuitive interpretation, as I was saying, so that this expression at any value of lambda, so the lambda increases monotonically from lambda I to lambda f as you move along this path. So for some value in between, say you're here, so here you have some, say, lambda, just lambda. Then this expression inside, or this expression including the square root, this is nothing but the norm of this tangent vector. Okay, so the norm of this is dx mu d lambda dx mu d lambda square root and all derivatives measured at lambda. All right. And then here, all I'm saying is that you sum over all these lengths. You take all these infinitesimal vectors, you sum them up, that gives you the length of this curve. I mean, I hope this makes sense to people. Okay, so there's one question. So Carol mentions that the parameter must be affine for the equation to be true, but I don't understand the reason for that. So this equation as an equation for a straight line is true regardless of your parameterization. But this equation as an equation for the geodesic is only true if you have a certain parameter. I hope I will get to that today. Let's see. Okay, so this is going to be my length of a curve. I'm going to specify this by S. All right. Now, our problem is to find a path connecting 2 points, these 2 points, which are fixed, which has the smallest length out of all possible paths, right? So there are many paths connecting these two things. That may be very complicated. So which one is the shortest? How do we find these things? Well, so again, we have to rely a bit on our calculus course. Whenever we have a function of some variable, and we want to maximize the value of that function or minimize the value of that function. So we want to find the value of the variable for which the corresponding value of the function is an extremum. We simply compute the first derivative of that function and set that to 0, and then solve for the value of the parameter such that that equation holds, right? So here we want to do something similar. So this is the thing that we want to extremize. But what is this a function of? This is a function of path, right? So given a particular path, you can write down an expression like this, which will give you a number. So given a different path with the same initial and final point, again, you can compute this and get a different number. So basically, and like I say, recall that the paths are, again, just a set of functions x mu of lambda, right? So this S is really a function of these x mu's, which themselves are a function of one parameter. So this is basically variational calculus. Now, I don't exactly know whether you have studied this. Maybe some of you have, maybe some of you haven't. So if you have studied this, okay, this makes sense. If you haven't, then just kind of try to understand the intuition that we have a function that measures the length of a curve. So this obviously is a function of the curve itself, right? Because if I give a different curve, you will have a different value of this function. And we just want to minimize or extremize really the value of this function, the value of the length of that curve. So we have to vary this, or we have to take the first derivative of this with respect to the curve itself. Again, if you have not seen this before, it may seem a little strange. How do you take derivative of something with respect to a curve? Well, so I can write down the formula, but I will not have time to explain these formulas really if you haven't seen them before. But basically what we want to solve is that we set up this variational problem that the functional derivative of this delta S with respect to delta x mu, which is a function of lambda, we set this to 0. And this is the analog of setting the first derivative of a function with respect to its parameter to 0 to find its extremum. Now, regardless of the functional analytic technicalities behind these derivatives, there's a very easy prescription for how to compute these things. However, that gets a little complicated in this example because of the square root. Now, there are many tricks to avoid having to deal with the square root, okay? I am going to show you one trick, but it is by no means unique. There are many tricks. So the trick that I'm going to use is the following. I'm going to define a new functional, and I'm going to call it SP, which depends not only on these x mu's, but also on a new scalar function, E. And this will look like, I mean, I'm just defining this. I'm pulling this out of a hat. I will justify this definition later. These x's are also functions of lambda, but it gets a bit messy if I keep writing it down. I mean, so is this. This is a function of x, which is a function of lambda. Anyway. So if you compare these two expressions, this and this, they're quite similar. You have the same initial and final values. Here you don't have this square root, and you have this extra factor in front of this term, and you have this extra additional term. Okay. Now, why is this function better? So this depends on two kind of things: these x's and this new thing that I have introduced. Okay. So I can extremize this with respect to both x and e. So what happens if I extremize this with respect to e? So suppose I take the functional derivative with respect to e, and because if you know how to take functional derivatives, you will readily notice that this is nothing but this. And when we're extremizing, we set the functional derivative to 0. So this tells you that this functional s is extremized with respect to e when e takes this particular critical value. I'll write it as e critical, and that critical value is, I mean, we just solve this equation for e. So you have the square root because here you have e squared, and then you just have this. All right. So now if you substitute this critical value of e back into this functional, so here you have 1 over e, and e is square root of this thing, basically square root of this. So after substitution from this term, we will have the square root of this thing. And this again is the same expression. So you have two of those things, and there's a half here. So you will end up with one copy of this g and then this thing, right? Which is exactly the same as this expression. So the point is, the new function that I defined has this nice property, sp x mu e critical is the same as the original s, which only dependent on mu. So now if I extremize this with respect to x, it's the same as extremizing this with respect to x, right? So now we rely on the idea that when you're extremizing a function with respect to its arguments, it doesn't matter which argument we extremize first. So instead of extremizing this first, we could have extremized this. And it's easy to extremize sp with respect to x because there are no square roots. Okay. So we can easily compute these quantities. I have to skip some computational steps, but well, okay. The first step is, so basically you find that this is equal to this. Okay. And then we still have to extremize with respect to e. But we already know the critical value of e, which is this. So we can just substitute that here and here. So if you do that, substitute e critical. So then what you find is that this expression becomes this. Okay, so obviously there are some computational steps here, which I'm skipping. But this is routine computation, like it's just taking functional derivatives. You may wonder, where is this Christoffel symbol coming from? There was no Christoffel symbol anywhere here. But notice that there are derivatives of the metric, right? And now if you recall our definition of the metric compatible Christoffel symbol, it also involves derivatives of the metric. So if you carefully do this variation, all these derivatives of the metric, they will combine to give you this Christoffel symbol, okay? So you end up with this expression. And recall, this is simply the first derivative of this functional with respect to these coordinates. So in order to extremize, you set this to 0. So you set this to 0. And this then is your equation for the shortest path, right? So what this means is that a curve connecting 2 points, a curve being a collection of functions of lambda, is the shortest path between those 2 points if these functions of lambda satisfy this differential equation. All right. So if you now compare this with our equation for a straight line, which was this, these terms, they do appear in this equation, right? They're the first 2 terms. But we have this additional term, which was not present in the equation for the straight line. So what is going on? So this, by definition, is our geodesic equation. And as we are clearly seeing, let me actually copy this straight line equation so that it becomes easier to compare. Okay, so we have 2 very important differential equations. So one that defines a straight line, and another that defines a geodesic, the shortest line. And they don't seem to be exactly the same, right? But what is their difference? Their difference is very interesting in the following sense. This difference is proportional to the tangent vector, right? So remember the physical interpretation of this equation. This equation was telling you that the tangent vector is being parallelly transported. So the covariant derivative of the tangent vector was basically 0. This is the covariant derivative of the tangent vector. So this basically is dx mu d lambda covariant derivative. The free index is mu. Let me use mu. Right. And so what we observe here is that the covariant derivative of the tangent vector along the shortest path is not 0, but it is proportional to the tangent vector itself with a proportionality constant. So notice that there are no free indices here. So this is important. This is a scalar. And this is the tangent vector. So we can kind of summarize what we learned from this as the following. So a straight line means covariant derivative of tangent is 0. The shortest line means the covariant derivative of tangent is proportional to the tangent. Okay? But now I want to make the claim that these 2 conditions define the same curve because of the following reason. So suppose you have this curve and you have this tangent vector at some point. So the covariant derivative of the tangent vector tells you how this tangent vector is moving along these directions, moving along the curve itself, right? So if it is proportional to the tangent vector itself, then this is moving in the same direction. I mean, this is moving in the same direction that it is pointing toward, right? So the covariant derivative of this is proportional to this. So this is moving in the same direction. And if you keep doing that everywhere, you will never leave this line, right? So you will always be on this line. So what I'm saying now is, of course, completely non-rigorous and just intuition. So I will actually give you some exercise problems where you will work out the exercise that proves that these two lines are the same. But for now, let's just try to build intuition that this equation is telling you that these tangent vectors, as you move along these lines, these tangent vectors remain proportional to the tangent vectors, to themselves. So basically, you are never leaving these lines, right? So if you move this, I mean, it doesn't change direction in the sense that it remains tangent. This was simpler because it simply said that this covariant derivative do not change, which means that in addition to remaining tangent, they kind of also keep their sizes fixed. So this just allows you to change the sizes of the tangent vector, but they do not allow you to deviate from being tangents. So both of them define the same curve once you integrate the whole thing, but the size of the tangents are different in these two descriptions. So the quantitative statement is that these two descriptions differ by a choice of different parameters. And to really understand what that means, you have to prove that quantitatively how to relate these two equations. And again, that requires some computational steps, which I will delegate to an exercise. So today, let me stop the lecture here with these two very important equations that we are going to use in the next lecture to understand curvature and some physical interpretations. But so just what was the upshot of today's lecture? So remember that we have derived two differential equations for the coordinates, which are going to be function of a parameter defining a path. And these two differential equations, the solutions of them define some very important class of paths, namely the geodesics, the shortest paths between 2 points, and the straight lines, the curved analog of the straight lines. Okay, so I will stop here and see if I can answer some questions. I have seen this similar technique in path integral formalism in QFT2. I have a question regarding this auxiliary function we are talking. What is its nature? It's definitely not a scalar because of how it transforms. I introduced it here, I think. Well, I have not really written down how it transforms, but it is a scalar. It will transform like a scalar. And I have not said anything about its physical meaning, but I can say that. So let me first make the statement. So this corresponds to the metric on the line. Now, I don't want you to think too much about this statement in order to avoid confusion about the metric of the spacetime with the metric on the line. But the point is that you can choose an independent metric on the line that has nothing to do with the metric on the spacetime. And a line is a one-dimensional thing, right? So in a d-dimensional manifold, your metric is a d by d matrix. So in a one-dimensional manifold, which is a line, your metric is just a scalar. It's a one-by-one matrix. And it is that thing. But yeah, you don't have to worry too much about it. And indeed, if you study QFT or in particular in string theory, then you will see this kind of tricks being used to simplify actions. We used to get rid of the square root form. Yes. Does a geodesic equation just add a scaling factor to the tangent vector while straight lines preserve its norm? Exactly. Kindly share the notes. Yes, I will upload my notes, the PDF version in Slack. I guess the scaling also helps minimize the functional as the curve does. That's right. So the scaling is maintained in such a way that the curve maintains minimum distance. But okay, yeah. Well, the basic intuition is that, so here we are using some parameter lambda to define our path, right? But you could choose a completely different parameter. So basically what we're saying is that we have some parameter lambda which takes different values at different points, lambda 1, lambda 2, lambda 3. So let me be even more explicit. So maybe lambda is 0.1 here, and then 1.2 here, and then 5 here. But I could choose a different parameter, mu, which I can use a different color, which may be like minus 100 here, and then 500 here, and then 1011.7 here. I mean, how you parameterize a line, or basically how you label the points of a line, doesn't change what the line is. But this kind of reparameterization will change these differential equations. And they will exactly change this differential equation by adding a term on the right-hand side proportional to the tangent vector. And so basically, starting from here, you can find a different parameterization such that this term goes away, and you end up with this equation. Any additional recommended lectures for these? So basically, all I'm saying, so most of what I'm saying is from Sean Carroll and Ward's book. This particular derivation is not from the books, but they have a different derivation. So, well, okay, so this derivation, well, I haven't really shown it the derivation. Okay, I will try to find somewhere it's written down. Well, or I can send you, if I can find something, I will send you my handwritten notes. I mean about transformation under reparameterization. What was the original question? Is an auxiliary function dependent on the parameter in your system? We use it to get rid of, oh yeah, that's right. If you choose lambda such that lambda is the distance along the curve, then the scalar, the derivative of log thing will vary. Exactly. So there is this result that if you choose lambda to be what is called an arc length parameter, meaning that the value of lambda at any point is really the length of this curve up to that point, starting from some initial point, then the tangent vectors are always unit normed. So this is always 1. So this vanishes. So in the arc length parameterization, the geodesic equation is the same as the straight line equation. I think this is similar to how we get rid of the square root in the Namagoto action. Precisely. So this original action is the one-dimensional analog of the Namagoto action, and this is the one-dimensional analog of the Polyakov action, which is why I wrote this P. I think, could we not do the extremization calculation directly without the E lambda? Absolutely, you could, and that's how I think Sean Carroll tries to do it, but then he tries to simplify it using the arc length parameterization. But I don't think you have to use the arc length parameterization. You could just directly vary this action and derive the geodesic equations without any trick, just straightforward brute force computation. This will work. It's just a little more work. Okay, I think that's the end of the question. So maybe we can stop now and yeah, let people go.